Hello, everyone. Today, I'm going to present our recent work on attentive federated learning approach for short-term residential load forecasting. This is a sub-research problem under the project Physics-Aware AI-based approach for cyber intrusion detection in substation automation system, which is sponsored by C3AI Digital Transformation Institute. My name is Yang Yu, and I'm currently working as a postdoc researcher at Division of Network and System Engineering at KTH. This is a joint work between me and my supervisor, Professor Carlo Fisconi. First of all, I would like to talk about the general load forecasting problem and the research motivation. In the smart grid system, the operator needs to know the energy demand of different parties in the grid so that better coordination can be achieved among different parties. In this case, we need to do the load forecasting. Let's take a look at the example. In this figure, there's a central server which is coordinating with several smart grid consumers. For example, these residential households, these factories, and these companies. This central server is also coordinating with several power plants, such as this wind power plant and this traditional power plant. The load forecasting problem here actually refers to that the central server needs to be able to predict the future energy demand of these smart grid consumers. In this case, it can better coordinate with these smart grid, these power plants to decide on the right amount of energy that needs to be generated, distributed, or transmitted. To be able to make the prediction, the central server needs to gather or collect the data via this smart meter and further utilize the AI-based techniques to train the forecasting models. In this work, we are mainly focusing on the short-term residential load forecasting problem. There are two main challenges for this problem. The first one is that the load profiles of different households would be strongly affected by different human behaviors. In this case, the load profiles can be highly variable and difficult to be predicted. On the other hand, these load profiles are also affected by the diverse external factors, such as these weather conditions, economic conditions, the working day or the holidays, and something else. The efficient way to solve this is to utilize the advanced data analytics and the machine learning algorithm to discover the underlying hidden load patterns based on the historical load data. And the performance of the load forecasting problem, in this case, can be significantly improved. The traditional way to do this is to train the local model by only using the local load data. But this will suffer from the overfitting issue when there is a shortage or there is a lack of local data. To address this issue, people have proposed to use the global training method. For this global training method, the central server needs to gather or collect the data from all the households, and the global model is trained or learned in a centralized way at the central server by utilizing all the available data from the households. And this will actually cause the privacy risks, since the private information of the individual households will be exposed to the adversary during the data transmission process. Recently, people have proposed to use the federated learning approach as a privacy-preserving solution. Here is an illustration of the FL process. For the FL process, the model is only trained locally with using the local load data. There is no data exchange. The only thing that is exchanged between the client and the server is the model parameters. So there is no privacy risks. When we apply this federated learning approach to this load forecasting problem, there is a severe issue, which is caused by the distinct load profiles of different households. Since the federated learning approach is based on the assumption that the data we utilize in this process is identically and independently distributed. However, this is not the case for the smart grid. Since, as we mentioned before, the load profiles or the load patterns of different consumers or different households will be different since the energy consumption of different consumers or households is different. To this end, we need to modify this traditional FL framework to make it more personalized or more fine-grained, such that it can fit for predicting the load for each individual household. In this paper or in this work, we do 3 steps. The first step is to do the clustering. And in this step, we cluster the households into multiple groups based on the similarity of the load profiles. In each cluster, the load profiles of different households can be approximately regarded as IID. In this case, the FL can be performed in each cluster to get the global model for each cluster. Due to the imperfect clustering, the households in the same cluster would still have diverse or distinct load profiles. In this case, we wish to mitigate this negative influence of this non-ID load profiles. And in this work, we propose to use the content-aware client selection scheme for the into the predictive learning process. The main idea of this client selection scheme is to select the households that with the representative load profiles in this cluster to participate in this FL process. And the data that are utilized in the FL process would be more IID compared to the case when using all load profiles of all households in the same cluster. To be more specific, the client selection is achieved based on the criterion that we want to find a subset of clients whose weighted gradient aggregation can approximate the full gradient aggregation over all clients. In other words, we wish to find a subset of clients that can minimize this gradient estimation error. The previous two steps are proposed for mitigate or reducing the negative effect caused by the non-ID load profiles. And now in this third step, we wish to modify the global model that is obtained after the first two steps, to make it more fine-grained or more personalized, such that it can better characterize the distinct or diverse load profiles of each individual household. To this end, we propose to incorporate the alternative model aggregation scheme into our FL framework. The main idea of the alternative aggregation scheme is that we wish to pay more attention to the household with a relatively different load pattern compared to the majority of the households in the model aggregation process. And in this case, we would like to modify the global model more to the direction that can better characterize the specific household with relatively different load pattern. And now let's have a look at this our numerical experiments. In our experiment, we mainly test 4 different algorithms: the traditional or vanilla FL algorithm, the cluster-specific FL, and the specific FL plus the client selection scheme. In the end, we tested the attentive model aggregation that is built upon the cluster-specific FL. For the first figure, we are testing the performance for one specific user using the model that is trained by all available data from all users. As we can see that for this case, the prediction accuracy is quite low, and the gap is still very large. To improve this, we first propose to use the cluster-specific FL, so which is shown in the second figure. For this approach, we first cluster all the users, all the households into different clusters. Then we use the data in the cluster, data from the households or from the users that are in the same cluster with that specific user to train the global model. And as we can see from the figure, the performance is improved a little bit. However, there is still a large gap between the predicted value and the true value. The reason is that, as we mentioned before, there is because of the imperfectness of the clustering process. To further mitigate this this negative effect of the non-ID load profile, we add a client selection scheme into the third figure. The third figure shows that by utilizing the client selection scheme means that we select the representative household that are with the representative load profiles, and only allow these households to participate in the FL process. We can enhance the performance of our algorithm to some extent. You can say that the gap between the predicted load and the true value has been decreased. In the end, we add the alternative model aggregation scheme to our previous framework. We can show that the alternative model aggregation scheme can improve the performance when we use the global model to predict the certain specific household, which means that the alternative model aggregation scheme can help us to modify the global model such that it better fit to characterize each individual household. So now it's the conclusion. So the first conclusion for our work is that the cluster-specific training with client selection can mitigate the influence of non-ID load patterns for the FL process-based load forecasting. The second conclusion is that the alternative aggregation can help to get more fine-grained model, global model, such that it can better characterize the load patterns of each individual household. That's all for my presentation. Thanks for listening.